Welcome to the Advanced Analysis and Data Science session of the Virtual New Zealand User Conference 2020. My name is Claire Thurlow and I am the GIS Education and Training Manager at Eagle Technology.
Yeah, and also on behalf of me, thank you for joining this session. My name is Boudewijn Boogaard and I'm part of the Technical Solutions team at Eagle, based in Auckland.
Boudewijn and I are going to take you through some exciting aspects of analysis and data science in this session. But before we do, if you'd like to ask any questions specifically about this session, please do go to the Ask Question, which is right down at the bottom of your side panel in the virtual platform. And make sure that when you submit your session, it has selected Analysis and Data Sci in the drop-down menu. While we're on the subject of questions, for those of you who ask questions about plenary subjects, these are being collated at the moment and will be released into the virtual platform by the end of the day. So you will see those under the Resources tab in the virtual platform. So by the end of this session, we are hoping that you will have a better understanding of what data science is and how you can apply analysis to the roles that you might currently have or the roles that you might undertake in the future. So let's go. First up, we're going to define data science. It's sort of words that have come about and emerged in our industry over the last couple of years. But do any of us really truly know what they mean? So maybe we can help by saying data science is the use of scientific methods, processes, algorithms, and systems to extract knowledge and insights from data. Analysis is an integral part of data science, and data science is multidisciplinary. Because we are GIS professionals, the focus of this session is on the use of spatial data to obtain knowledge and insights. We are therefore technically looking at spatial data science. So to help us out on our journey, we have defined some building blocks of data science. And we're going to use these to structure the session. These building blocks give us a workflow from where we perform analysis in the ArcGIS platform. It might be that that is in ArcGIS Online, in ArcGIS Pro, or in ArcGIS Enterprise, or even by connecting to third-party software and the Internet of Things. Realistically, the actual analysis process is not linear like we're seeing on the slide here with the building blocks. It's iterative. Before we even jump into the building blocks, however, we obviously need to have a reason for doing our analysis. So a problem that we want to solve. This problem could range from where should I put a new ski resort to locating road segments that have a high risk of crashes occurring on them, to how do I train a computer to scientifically identify potential locations in reintroducing green lip mussels in a harbour. And also on top of having our problem, we want to have some data that we can actually use to solve that problem. So let's have a look at these building blocks that we've defined. So the first building block is data engineering. This is often when we spare the most of our time when we're doing analysis, and it involves manipulating our data to make sure that it's suitable for analysis. It could include adding fields and maybe even adding a spatial component to our data. Our next building block is visualization and exploration. This building block allows us to explore our data and better understand it so we can use it to perform analysis. Basically, we're getting to know the data, understand it, to get a sense of what problems we can solve with it. The visualization part of this building block can play a role throughout our workflow and analysis. For example, we might use analysis or we might use visualization to share our results of our analysis. Our third building block is actually a huge subject in itself, and that is spatial analysis, machine learning, and AI. This building block, within its 3 different parts, uses algorithms and equations to break down the problem that we're trying to solve into pieces. It helps us to analyze our data, quantify the patterns that we are seeing, model the phenomena we're seeing around us, and turning data into information and gaining understanding. Our fourth building block is big data analysis, and that's basically taking our third building block and expanding it to big data sets. And those data sets might be massive imagery collections, huge vector data sets, or real-time data that we need to analyze to get some information. And Esri is continually working on expanding their capability in the area of big data analytics. Our fifth building block is modeling and scripting. We already have existing tools that we can use, or models that we can use to model complex phenomena, and we can automate processes using this building block, and we can also extend existing functionality with modeling and scripting. And last but not least is our sharing and collaboration building block. Because really there's no point in doing analysis if we don't share our information that we get from the analysis with other people, or maybe even share the processes and workflows that we've gone through to get that result. Therefore, sharing can include things like using story maps or dashboards to share our results or our processes.
All right, thank you, Claire. So now we had a look at all the building blocks, and I want to go through the building block one by one. And I want to start off with data engineering. And data engineering is perhaps not the most exciting task. I mean, it's all about cleaning your data, getting it ready to put into a tool or a model. And it can include everything from a simple field calculation to geo-enrichment to add additional attributes and context to the analysis. And for that reason is one of the most important parts of the process. And before we do any data engineering, we have to ask ourselves, what is our analysis question? And then what data do we need for that? And also what data do we have available to us? And for that, there are different sources available. It can be data that's available in ArcGIS Living Atlas, like demographic data, boundaries, satellite imagery data. And there are also many other sources you can get data from, things like LINS or NIWA, or data that you've collected yourself. Also, the internet is a great source of data as well. And in almost all cases, you'll need to engineer the data to be able to use it in your analysis. And a lot of data that you'll find isn't native geodata. Sometimes it has an address, or it's a table with XY coordinates. And sometimes it's just an attribute, like a city name or region. And in many cases, you want to geo-enable it, either by geocoding or matching the attributes to another data set that has a location. And again, in other cases, you may want to enrich your data with more attributes coming from a different data source, for example, a demographic data set. Another thing you want to do is check your data for missing values. Or even incorrect values, because that can affect your analysis. And in the last year, a lot of work and improvement has gone into the data engineering experience inside ArcGIS. For example, through the cross-platform integration of notebooks, optimizations in ArcPy and the Python API. And you'll be seeing many advancements on this in the next releases as well, as it's one of the focus points for Esri to work on. And ArcGIS Notebooks is one of the very useful tools to data engineering, because it brings the power of Jupyter Notebooks and Python inside of ArcGIS. And it's available in ArcGIS Pro, ArcGIS Enterprise, and since the latest release, also in ArcGIS Online. So let's have a look at an example of this in ArcGIS Pro. In this example, we'll download the current COVID-19 cases from the website of the Ministry of Health. We'll do some data engineering and then publish the data to ArcGIS. And here we're looking at ArcGIS notebooks in ArcGIS Pro. If you've used Jupyter notebooks before, it will look very familiar. You have the notebook toolbar that allows you to add, edit, and run cells. And the great feature of notebooks is that you can create cells for text, images, and code, allowing you to give context to your workflow. You can also output the results quickly as a table, charts, and maps. Let's have a look at some of these features. So we'll start by importing the necessary libraries like Pandas and ArcGIS API for Python, and we connect to our portal, in this case ArcGIS Online, using our login from ArcGIS Pro. Now we need to download the data, and the data is published as an Excel on the website of the Ministry of Health and updated every day. And here we download a file and convert it to a Pandas data frame. And here you can see a snippet of the table in the output cell. The data contains a row for each case with information about the district health board that we'll use later to geo-enable the dataset. But first, we're going to modify the table. We'll drop and rename some columns, change the time to UTC, and group by DHB and the date. We'll also calculate the daily differences and output the results in a table shown here. In order to geo-enable this dataset, we'll use a point dataset that represents the DHBs. And this was created before using some data engineering and then published to ArcGIS Online. So I'll grab this layer from ArcGIS Online and convert it to a spatially enabled Pandas data frame. And this is similar to a normal Pandas data frame with the difference that this dataset has a shape field with the locations of the DHB. And this dataset also has information about population that we'll use later on. We can also output the results on an interactive map in the notebook. And here we see a point that represents all the quarantined cases that don't have a specific DHB assigned to them. Next, we'll do a simple join to add the geometry to our process table. Here, we'll also use the population to calculate the number of cases per 100,000 population. And now we have a data set that can be used for further analysis. We can publish it to ArcGIS Online or ArcGIS Enterprise and share it with our analysts.
Thanks, Boudewijn. Let's now have a look at our next building block, which is visualization and exploration. With this building block of data science, we're trying to make sense of our data. Why? Because knowing our data helps us determine what type of analysis, machine learning, etc., we might want to apply to the data, even if the data is appropriate to have analysis applied to it. Rather than talk about the techniques of visualization and exploration, let's actually have a look at some real life data.
So here we are in ArcGIS Insights, and I'm going to take you through some data exploration and visualization for crash data in New Zealand for the time period of 2012 to 2018. I'm particularly interested in this data because I work for the police or the council as a roading engineer, and I want to keep people safer on our road systems. On the left of my screen here, you can see a card which shows the spatial location of all the crashes in New Zealand. It's displayed as a heat map, and not unsurprisingly, we can see here in Auckland that we have a hotspot of crashes, and then we have one in Christchurch and potentially one in Wellington as well. Not only in ArcGIS Insights can I look at things in a spatial view, I can also explore the attributes behind the data. So to the right of my screen here, you can see a series of graphs, and I have graphed the accidents that are happening per year. And the spikes in the number of accidents in 2017 and 2018 here in my bar graph have me a little concerned as to why I have so many extra accidents happening in those years, which would mean that I might want to go and explore some more as to that reason. I have looked at each individual year as well. So I have the crashes here in a line graph for 2018, and I'm a little bit concerned because the last accidents I have this year are in August. So I might want to go off and find some data for the end of 2018. In 2017, I am concerned because I have some spikes here which are taking me down very close to 0 crashes in this time period. So I have some further exploring that I need to do for crashes in 2017. My 2016 data, on the other hand, I'm happy with. The spread's good, time periods are good as well. But you can see just from 4 graphs that there might be need for me to go back to my data engineering building block for data science. Some of the other attributes that I might be interested in looking at could be or the time of the day that an accident happens. And in my bubble diagram here, you can see that my red bubbles are showing when the time of the day that most accidents occur. So from 3 p.m. to 6 p.m. I'm also interested in the day of the week. So I'm going to create another chart here. I'm going to create a donuts chart, and I'm going to use the day of the week as the item in my donuts chart. And surprisingly, most days of the week here seem to be having approximately the same number of accidents happening on them, with Friday being a little bit bigger and Sunday perhaps being a little bit smaller. The last attribute I have explored in ArcGIS Insights is speed of traveling when the crash occurred. And I've got a summary view in this box and whistler graph, but also a bar chart here that shows us individual speeds. And you can see we've got a spike here close to 50 kilometers per hour and another spike here close to that 100 kilometers per hour. So ArcGIS Insights doesn't let us do all the visualization and data exploration that we might want to do. So I've swapped over to ArcGIS Pro just to show you a few extra items. So at the bottom of my screen here, you can see that I've got a data clock. And this data clock allows me to show in concentric circles every year of my data and also every month of my data as the segments. And you can see that March consistently has a lot of accidents happening in that month across all years. We can obviously look at particular locations of the crashes, but I've also done a little bit of analysis here to confirm what we saw in our heat map. So I've run a hotspot tool, and I have statistically significant hotspots in Auckland, Christchurch, and to a lesser extent in Wellington. So let's zoom in on one of these locations. We're going to go to Christchurch, and I've just done another hotspot piece of analysis for the centre of Christchurch. And not unsurprisingly, right in the centre of Christchurch, we're seeing more accidents happening. I wanted to see if there was any change in those hotspots over time. So I've done an emerging hotspots analysis. And if I just zoom in a wee bit closer here, you can see that we have a number of new hotspots in our data through time. We have a number of oscillating and sporadic hotspots, and we also have some consecutive hotspots. So if I was a roading engineer for Christchurch City Council, I might be wanting to do some analysis on the new hotspots and the consecutive hotspots to see what were causing the crashes to happen in those areas. The other way that we can visualize this emerging hotspots is to take it into 3D. And so I've created a 3D visualization of emerging hotspots as well.
Right. Thanks, Claire. As you can see, ArcGIS Insights is a real powerful tool to explore your data, and it even works for non-GIS analysts. And many new capabilities have been added to ArcGIS Pro as well to explore your data through charts, but also with spatial analysis tools that allow you to analyze it through space and time. Now let's talk about the spatial analysis, the methods and algorithms that allow you to solve spatial problems. And within that also falls machine learning and AI as one of the approaches to solving spatial problems. And here we bring these concepts together, spatial analysis and machine learning, because the reality is that it's nobody's problem that they need machine learning. The focus is on the spatial problem solving, regardless of the method. And whether it's a more traditional GIS technique like weighted overlays, statistical analysis, or deep neural networks, the focus is on problem solving. And within ArcGIS, we have a lot of approaches to solving these spatial problems. There's this underlying geoprocessing framework that allows you to manipulate and understand your spatial data. And within this framework, you have the more traditional approaches to solve spatial problems, things like suitability modeling and spatial statistics. And there's also a lot of machine learning approaches with tools for doing predictive analysis, pattern analysis over space and time, all the way into deep learning for object detection and extraction. And even though there are a lot of tools available in ArcGIS, you sometimes have to reach out to other possible methods to solve your problem. And luckily, there's this rich data science ecosystem out there that you can take advantage of as well. So Esri is working really hard to build bridges between them, whether that is by using Python to easily use libraries like pandas or machine learning libraries, or through the ArcGIS R bridge to be able to use all the packages available in R. And machine learning has for a long time been integrated in ArcGIS. But in the latest releases, you see more and deeper integration with machine learning and deep learning libraries, where you can leverage the machine learning through your familiar tools in ArcGIS. And now we're going to see a couple of different examples of spatial analysis. And we'll start with Claire.
So we're going to start with talking about what spatial analysis actually is. We're bringing spatial into problem solving efforts. And obviously, as spatial professionals, that seems like an obvious thing to do, but sometimes people outside of our profession don't take spatial into consideration. When we're talking about spatial analysis, we're taking questions, spatializing them, and using a set of analytical methods and algorithms to provide it out of the box by Esri to provide answers to these questions. With spatial analysis, we could be performing site selection, finding clusters, making predictions, and or quantifying patterns that change over time. So let's have a look at a couple of spatial analysis examples. The first example I want to show you is a site selection example. And this is actually undertaken by school children in ArcGIS Online when they are doing NCA Level 2 Geography or are in Year 12 at school. They're looking at where to site a suitable ski resort inside of the Mackenzie District Council. The criteria that they have is that it needs to be on land that is between 1,300 and 1,800 meters in elevation, within 10 kilometers of a major road for accessibility, between 40 and 60 degrees slope, which is identified as being ideal slopes for advanced skiers. The students perform some overlay analysis to get a suitable site layer. The actual results that they get is quite extensive. So they are asked to think about what else or what other criteria they could add to focus the suitable sites. Sometimes students come up with different answers, and they could include the presence of snow during winter. Is the land inside or outside of a national park? How close does the site to existing services to service a ski resort? This particular piece of analysis is done with vector data in ArcGIS Online. Typically, this type of data or this type of analysis is done with vector data. And you may be interested to know that raster analysis is available for ArcGIS Enterprise. And hopefully that means that it will soon be available inside of ArcGIS Online as well. Now let's switch to ArcGIS Pro to see a little bit about suitability modeling there. So if any of you have ever been to university and done a GIS paper, you will note that suitability modeling is a core part of the things that you do. However, with the release of ArcGIS Pro 2.6, suitability modeling has just become easier with this really cool new tool called the Suitability Modeler. This tool takes all the standard rasters that you would traditionally manually analyze for suitability modeling and allows you to interact and change classifications on the fly for individual layers through the bottom pane of this graphic called the transformation plane. This automatically updates the individual raster as well as the raster that shows areas that are suitable for the item you are searching for. This suitability modeler performs weighted suitability analysis. To see some more about the suitability modeler, watch the video from the Esri UC, which is available for general viewing at the URL you see on the slide. And just in case you're wanting to do suitability modeling in a browser, don't forget the Suitability Modeler widget in ArcGIS Web App Builder. So now I'd like to pass over to David Haberkorn from Powerco, who's going to take us through how Powerco use spatial analysis in their overhead renewal planning tool, which just won the See What Others Can't story map competition at plenary this morning. He's going to start by explaining why they created this particular tool.
The Powerco footprint covers a large geographic area of the North Island of New Zealand. The networks in these areas have been in the past constructed by 18 different electricity distribution boards. Therefore, there's a diverse number of different material types and different network configurations in the way the networks have been constructed. As the Powerco networks are that diverse, and reconstruction solutions can be unique to different parts of the network, a tool was required to identify these needs. We also needed to consider current defects, asset condition, and type issues, as well as including the identification of risk and consequence to all stakeholders. With the expected increase in the renewal CapEx spend, streamlining the project production process and providing accurate data and engineering tool was required. Without a different way to identify projects, we could foresee large bottlenecks occurring at the planning stage and therefore not being able to deliver the Powerco 5-year renewal plan. Well, we started really simple, to be honest. One of the basic concepts of a geographic information system is to overlay different layers of information on top of each other. And that's exactly how we started in our first sprint, just by displaying, filtering, and overlaying different sources of information, and then creating new layers and maps for our planning engineers. That's how it all started. And looking at the map you see here, it's not exactly pretty, but it can be very powerful for someone who is only used to work in spreadsheets. From there on, we started to do more exploratory analysis on how we can create heat maps in a consistent and meaningful way. In the past, our engineers have played around with rigging tools and similar to create heat maps of, for example, defected assets. This, however, was not very intuitive for them, and also the results were varying. So we came up with the approach of using hexagons in different resolutions to create our heat maps. We simply display counts per hexagon, which we then normalize. While this is a very simple approach, it is also very consistent, repeatable, and turned out to be very useful for our planning engineers. We have then used this approach to not only create hexagon datasets for programmatic assets, but also for criticality and risk, as well as for all sorts of environmental data. Our conductor model then, on the other hand, is a bit more advanced. We have built a range of different models in order to implement the common network asset indices methodology, also known as SNIME, in order to predict our conductor health on the network. While this methodology is more advanced than what we did with our heat maps, it's not exactly rocket science either. At the end of the day, it all comes down to solid geospatial analysis and using the right tools for the job. Well, we are in the lucky position to have most of the ArcGIS platform at our disposal. And that means that we could really get the maximum out of what we needed to achieve for this project. With ArcGIS Pro, ArcMap, and ArcPy, we have a very powerful spatial analytics platform to build solid models and tools that can also easily be used and tweaked by our asset engineers. Using ArcGIS Enterprise not only enabled us to share content across the organization, but also offered a myriad of different apps to build more content. We have used Operations Dashboard, Insights, Collector, and Survey 123, just to name a few. Being able to use that full circle of running analysis, sharing the results in maps and apps, collecting field data, and then feeding that data back into our models for verification and validation is very powerful. Powerco moved into an uplifting capital renewal spend in 2019 with the successful application for CPP, which stands for Customized Price Quality Path. The number of projects required for Powerco's single largest category of renewal expenditure is the Overhead Network Renewal Program. From only having 32 projects in 2018 before CPP, we ramped up our project production now to 130 projects for the 2022 CPP plan, which is a massive increase. The Overhead Renewal Planning tool has allowed the overhead planning engineers to be in a position of planning 3 months in advance before CPP to now having 18 months of advanced planning in the pipeline. The tool has allowed detailed and accurate projects to be produced, as well as dealing with the uplift of number in project requirement due to the increased budgets allowed. So we not only have a quite significant increase in quantity, but what's even more impressive, the quality of the projects that get created now has also increased. Well, I had a good think about that, and to be honest, I don't think I would change a lot in how we build the tool. However, of course, we have our challenges. Since we started building the tool almost 2 years ago, Powerco has migrated to a new ERP system. And that means that at the moment we are struggling a bit with accessing data out of that system to update our tool. That is definitely something we didn't consider when we started building the tool. Another challenge is that if you have to make changes that have sort of a downstream effect on your tools and scripts, that can be a bit painful. If you have a stream, for example, of 8 scripts and you need to make a change in script number 3, that may break scripts downstream that you have to fix, and it may be things like a field map in a spatial join that doesn't work anymore. Other than that, you can't really avoid making these changes, but we definitely will have a few changes come up because we only at version 1 really of our tool, although we already made some tweaks to it. We would definitely like to look into machine learning and AI to train our model outputs and to verify that with ground truth data that comes out of the field and sort of get a confidence level up about the outputs of our models. And we also have heaps of other ideas of what we can add or build in order to improve our tool. I would also like to reiterate though that it's not really rocket science on what we were doing here. I would encourage everyone to sort of get together with their business units and build these cool geospatial tools. Also, what really worked well for us was working in an agile way that really not only has brought different parts of the business together, but also we were sort of able to constantly deliver small pieces, and that worked really well. We had a really clear vision of what we wanted to achieve in the beginning, but through using to work in an agile way, our tools have grown organically into something even more than what we initially envisioned. And that's really fantastic because we have added quite a lot of value to the business.
Yeah, thanks to David for this. That was a great story. And it's also great that he highlighted that it's not just about the spatial analysis. It's also important to work with the business to understand the business needs for the analysis. And if you want some more information on this, you can find a link in the resources tab of the virtual platform that will take you to the great story map, the winning story map. And there he explains in great detail the workflow that they use to get to this result. And from that link, you can also access all the other story maps that were entered in the See What Others Can't story map competition. And they all have very nice examples of spatial analysis. And David mentioned machine learning already. So let's dive a little deeper into this. And we have asked Orhun, Aydin and David Yu from the spatial analytics team at Esri to talk about machine learning and deep learning. And more specifically, what machine learning techniques are available in ArcGIS.
Welcome to the Machine Learning in ArcGIS session. Today we will discuss machine learning methods in ArcGIS Pro and some demonstrations on how to use these tools for spatial problem solving. My name is Orhun Aydin, and I'm with the Spatial Statistics team.
And I am David Yu, a data scientist at the GeoAI team here at Esri.
I will start with defining what machine learning is. Machine learning consists of data-driven algorithms and techniques that can automate tasks such as regression, classification, and clustering. And in the next slide, I will discuss these three different types of machine learning approaches. Traditional machine learning pertains to methods that solve a wide variety of problems, and we see them in use every day. In addition to traditional machine learning, we see the rise of spatial machine learning, where space and its representations are becoming more and more explicit at the definition of the algorithm. We are talking about methods that can incorporate geography, that can incorporate shape, density of spatial units, contiguity, spatial distribution, so forth. Similar to traditional machine learning, we can divide spatial machine learning into three distinct categories in terms of different tasks we can do, such as classification, clustering, and regression. Going beyond the methods, if we're talking about applications of these methods to distinct problems, we are generally talking about three main tasks. The first one being descriptive analysis, where we describe the data so that we can understand it, we can summarize it, we can seek patterns in it. This leads to predictive analysis, where we are trying to form relationships between different variables to make a prediction. And prescriptive analysis pertains to analysis that we do to make decisions that are directly impacting our decisions, such as designing zones for COVID-19 clinics, allocating resources, so on and so forth. Let's talk about clustering. Simply put, with clustering, we are interested in grouping observations based off of a similarity. There are different types of clustering that you can perform in ArcGIS, and on the right, you can see different types of tools that you can do to perform these clustering tasks. In this demo, we will delineate popular neighborhoods in San Francisco Bay Area using checking data. The data you see on the map are pins from an app called Goala. These are check-ins. The idea here is finding a statistically significant dense areas from these check-ins so that we can describe areas that are popular. In other words, areas that have a significantly high number of check-ins. For this problem, we can use density-based clustering, which is a purely spatial form of clustering that exposes areas that have a high number of check-ins. Here we will use an HDB scan. The tool identifies clusters and also what it terms as noise, which are these gray points, which do not conform to the idea of a dense cluster. In other words, these are areas that are not as popular as the areas that are colored. Of course, check-ins also have time tags attached to them. Another dimension that we can include in our analysis is time. To do that, we can create a space-time cube. Here we can create a space-time cube by aggregating points, and the output of this space-time structure can be visualized in 3 dimensions like this. Here in the Z dimension, we have time, and we can see times and locations where there are high number of check-ins in these red spots. We can also evaluate this particular cube using a space-time analysis tool called time series clustering. With the time series clustering tool, we can divide this space-time cube into clusters that have similar time series patterns. And time series clustering tool found 3 distinct clusters. In order to understand what these time series clusters mean, we can also investigate time series cluster medoids, the representatives of time series. Here you will see that red cluster corresponds to areas with high foot traffic, and green, it corresponds to medium level, and blue are areas that have less foot traffic compared to other 2. And you can also see that they have different variations throughout the day. With regression, we are talking about finding relationship between a dependent variable and explanatory variable. The example on the left shows using simulated global climate models in the red grid to predict temperatures observed at weather stations given in these black points. There are different ways of doing analysis that pertain to regression in ArcGIS, and on the right you can see different tools such as empirical Bayesian kriging, aerial interpolation, so on and so forth. In this demo, we will explore uses of regression analysis inside ArcGIS Pro to understand house price drivers in King County, Washington. The data on the map is an old Kaggle competition, and when we investigate the fields, the variables that exist in this data, you will see that this data is quite rich in terms of different attributes of a house it contains, such as the sale price of a house, number of bedrooms, bathrooms, square footage of living, so on and so forth. And using regression analysis, we will relate different attributes of a house to its sale price. Once we have a relationship that can accurately predict the house price, we can use that as a house pricing model going forward. In this tool, we will use random forest implementation in ArcGIS Pro called forest-based classification and regression. This is a very flexible tool that gives you the flexibility to solve complex problems by incorporating different data sources. In this example, my main data set is King County house data that contains price, which is the variable I would like to predict. I have a large number of explanatory variables I will use, and this model will create a relationship between these explanatory variables and the house price. Note that some of the variables, such as the view and waterfront, are categorical variable. And this tool is very flexible in terms of its modeling of categorical variables. All you have to do is check categorical. We know that distance to a water body that contributes to the scenery of a house does impact the price. You can automatically incorporate other data sets, such as water bodies of Washington, as a training distance feature. The tool will automatically calculate nearest distances to water bodies and include it as an explanatory training variable. This tool is also very rich in terms of the diagnostics it provides, such as variable importance tables. It gives you the ability to fine-tune your random forest model, and it does give you the ability to validate your model and also assess the uncertainty of the predictions you perform. Here, I'm going to run this tool on training mode because I'm trying to understand the relationships between explanatory variables and the target variable. If I have another data set where I would like to predict prices, I can also use it to predict to a different feature. Or if I want to create a price raster, I can also output a predicted price raster from this tool. But in this demo, we will use a training mode. The tool is able to capture houses with high prices that are close to the water and houses that are more inland that have lower prices. We can also assess the uncertainty in our prediction by clicking this prediction interval chart. For houses with higher prices, our uncertainty bounds increase. The reason for that is expensive houses that are in multiple millions of dollars are not very abundant in the training data set, meaning that small changes to the random forest will make a big change in the predicted price for very expensive houses. And this prediction interval reflects that. The variable importance plot summarizes the importance of every predictor variable in understanding the house price. Here we see that square footage of living is the most impactful variable in determining the house price. So is the condition of the house and distance to water bodies. And the output of this tool enables you to understand relative importance of every explanatory variable on the variable that you're predicting. Random forest is just one example of a very rich tool set for performing regression. And lastly, with classification, we are deciding which category an object should be assigned to based off of a training data set. Unlike clustering, here we have a training data set that tells us what are some of the attributes that correspond to a particular category. In ArcGIS, we have various classification tools, some of which you can see on the right.
I'm now going to quickly switch gears and talk about some other interesting applications of machine learning within ArcGIS. That is, how can we apply deep learning techniques to computer vision tasks? There are 4 key imagery tasks when it comes to deep learning. Pixel classification, which is the task of assigning unique labels on a per pixel basis. Object detection, which is all about creating minimal bounding boxes that delineate objects of interest. Instance segmentation, which adds to pixel classification by also predicting unique instances of objects. And image classification, which assigns labels on a per image chip basis. All 4 of these key imagery tasks are supported within ArcGIS. Let's start with object detection as an example. In Kolawai Tonga, coconuts and coconut derivatives contribute significantly to the local economy. However, it takes a lot of time and effort and a large workforce in order to classify coconut palms. To automate this process, we can use deep learning tools and models in ArcGIS Pro to identify coconut palms and evaluate their health. We start off by creating training labels. As with any deep learning workflows, the quantity and quality of labels has a direct impact on the output of the model at inference time. We can train a deep learning model directly within ArcGIS Pro based on these labels. Alternatively, it is also possible to train a model using the ArcGIS API for Python. With both, it is possible to select from a set of pre-configured models. Once the model has been trained, it takes just another geoprocessing tool called Detect Objects using deep learning to perform inferencing or prediction over an entirely new region. With pixel classification, an interesting project is land cover classification. The Chesapeake Bay is the largest estuary in the United States, with about 18 million people living in this watershed. The Chesapeake Conservancy is a nonprofit dedicated to conserving landscapes and rivers and restoring the region's natural resources. To do so effectively, it manually created a land cover map that classified land use type from aerial imagery from the National Agriculture Imagery Program, also known as NAIP. The result is a 1 meter by 1 meter resolution land cover data for 100,000 square miles of land, and this allows for precision conservation. However, it took them 18 months to process, which meant that by the time this map was completed in December 2016, it was already out of date. As with object detection, the same tools would be used for creating training data and for training the model, with the notable exception that the model we select will be one that supports pixel classification, in this case, UNet. We would also run export training data using deep learning in order to convert these labels and imagery into a format that can be consumed by a deep learning model. Finally, at inference time, we can use the classify pixels using deep learning tool, as opposed to the detect objects using deep learning tool, which is used for object detection. In the output, we can see these beautifully classified rasters, and if you look closely, we can see that the model is even successful at identifying swimming pools as bodies of water.
Yeah, that was a great overview of the machine learning capabilities in ArcGIS. And good to highlight here as well is that more and more tools come available to make use of machine learning inside of ArcGIS. But you can also use the ArcGIS API for Python leverage all of the capabilities. So you can use it in Python to run the same models. Now, after these US examples, I would now like to talk about an example here in New Zealand. And David Knox from Linker Analytics has used machine learning to create a land cover layer for the entire Tauranga City Council area. Because Tauranga City Council needed an up-to-date land cover data set for the analysis of hydrological imperviousness and hydraulic roughness for overland flow for the city's stormwater models. And in previous time, this would be a manual task, and it would take a lot of time to create this layer for the 210 square kilometer area. But Linker used machine learning on the 10 centimeter resolution imagery that was captured in 2019 to extract 8 different land use classes. They used Python, TensorFlow, and Keras to build convolutional neural networks and train these using annotations created in ArcGIS. And after the machine learning produced the different land use classes, ArcGIS was used to vectorize and post-process all the results, like making sure that the output is all topologically correct. And the output has reached an overall accuracy of 90%, which is quite impressive, and produced over 1.1 million polygons. And this is now a layer that can be used in further analysis on the hydrological models for Tauranga. And if you want to learn more on how Linker Analytics can help you, please check out their section in the sponsors tab in the virtual platform. Right, now we talked about some of the ways to solve problems, and to be honest, barely scratching the surface of what is possible. It's worth mentioning that increasingly we got huge data that we're trying to deal with. So it's massive imagery collections, huge vector data sets, CSV files that are enormous, and we need to be able to start to analyze them. And there's a lot of power in ArcGIS to distribute and parallelize them. And I want to talk about a few ways in ArcGIS that can speed up your processing of big data, and some of the advancements that are made in ArcGIS. And the first of those is that with every release of ArcGIS Pro, more and more tools support parallel processing. So what parallel processing does is that a big processing task can be split up in smaller jobs, and it will allow multiple CPUs, cores, or processes to work on the big job at the same time, often resulting in faster processing times. And you can set the parallel processing factor in the environment settings of the tool if it supports parallel processing. And there you can specify the number of processes that are being used. So you can really leverage the power of your analysis. Then another one is the geoanalytics, and that allows you to analyze large amounts of data, vector and tabular data, and it uses Apache Spark in the backend to distribute the workload. And it has a collection of tools to identify patterns, find relationships, anomalies, and incidents in very large amounts of data across space and time. So you can, for example, reconstruct tracks or join data, and not just based on location, but on location and time. And geoanalytics tools are available for ArcGIS Pro in the geoanalytics toolbox, and they will run on local big data. And it's also available for ArcGIS Enterprise as geoanalytics server. And with geoanalytics server, it allows you to leverage feature layers, cloud storage, and you can also use multiple servers to analyze very big data sets. It also brings geoanalytics to the entire organization, because these tools are available in ArcGIS Pro, but also in the map viewer. And similar to geoanalytics, raster analytics allow you to process large amounts of raster data using image server. So you can use one or multiple servers to do your analysis on very large data sets. And it has a collection of tools to manage your data, analyze patterns, analyze terrain, use deep learning for object classification and object detection, as we saw before. And also tools for multidimensional rasters to find anomalies and do forecasting based on trends that come through time. And with image server, with image server Raster analytics, you can bring these analysis to the browser as well, because they will be available in the map viewer once you've enabled it. And then another way that big data gets created is through real-time data feeds. And it can be from stationary assets that report their status, or from moving assets that report their updated location as well. And ArcGIS allows you to ingest the data and analyze it on the fly, and then output the data as well. For example, send it to a feature layer or send alerts if certain criteria are met. And ArcGIS GeoEvent is the on-premises solution for ArcGIS Enterprise. And new is ArcGIS Analytics for IoT. And that provides a SaaS solution, so a services solution that scales to your needs without you having to manage it. And what it also does, it adds inbuilt option to do big data analysis on all the ingested data to find patterns and locations. Now let's switch to the building block modeling and scripting. And you may think that it's all about automation, and it is, but it can be more than just automating a workflow. It can also be how you're prototyping, or how you design your study, or how you frame your thoughts. And there are a lot of options available in ArcGIS. So first, why do we want to automate? Well, most of the time we want to save time by automating repeatable tasks, and hopefully also minimize errors, human errors that can come into play. And we want to take these complex problems and also solve them as quickly as possible. And that is where machine learning and deep learning can be especially valuable. Another reason could be that we want to extend or customize what ArcGIS can actually do. So we may want to tap into the 15,000 unique packages that the R bridge brings to us, or we want to pull packages from the vast data science community. Maybe Python packages that are just really helpful. And in ArcGIS, there are many ways to model and script your workflows. And I want to show a couple of these options here. So Model Builder, that we saw in David's presentation as well, is a very nice way to quickly automate your models, but also to document your workflow. And it's all done through a graphical user interface. And Model Builder has been around for a long time, but still new features are being added to Model Builder. And a few of those are, for example, grouping of parts of your model to better visualize complex workflows. You can also quickly add tools to your models by typing the name just from the Model Builder canvas. And also, if you use Model Builder to prototype or just capture your workflow, you can afterwards save the model as a Python file. So you can bring it into ArcGIS notebooks, for example. You may need to do some editing here and there, but it gives you a nice framework to create your Python file from Model Builder. And also new is that you can now schedule models from within ArcGIS Pro. So you can set it to run at a specific time or run them repeatedly at a designated time interval directly from ArcGIS Pro. So you don't have to go to the Windows Task Manager. You can set it up in ArcGIS Pro. In a similar way, you can use Raster function chains to create a chain of analysis tools for Raster data. So currently there are over 160 Raster functions that you can chain together. And you can extend this even further by creating custom Python Raster functions. Here, for example, you can see a calculation of the severity of burned areas from before and after satellite imagery. So you can use this Raster function in ArcGIS Pro and ArcGIS Enterprise, and you can rerun it on different rasters. For example, you got a new burned area like we have now in Twisel. You can grab some before and after imagery, run the same model, and it will give you a severity burn outcome. And then Python. And Python is a language that you can use throughout the platform. So for working with Python, you have ArcPy and the ArcGIS API for Python. And ArcPy is a very comprehensive, powerful library for spatial analysis, also for data management, data conversion. And in total, there are over 1,300 tools that can help you. And the ArcGIS API for Python has over 2,300 methods and functions, and that allows you to analyze spatial data, but also manage your WebGIS and perform spatial data science. It also gives access, so Python also gives access to that open data science ecosystem, because you can bring in Python libraries for your analysis. And then ArcGIS notebooks are relatively new experience in ArcGIS to leverage the power of Python. And whether that is for data engineering, visualization of spatial analysis, or for using deep learning. And it's integrated in ArcGIS Pro, ArcGIS Enterprise, and like I said, since the latest release, also in ArcGIS Online. So go check it out. And using ArcGIS Enterprise allows you to schedule your notebooks as well. And this is a feature that's coming soon to ArcGIS Online. And then there's also the R-Bridge that I mentioned before. And basically what you can do is combine the power of ArcGIS with the statistical capabilities of R. So you can bring in your spatial data into R, or you can extend your R models with ArcGIS to extend and enrich your data, analyze it with spatial algorithms, all of the tools that are available, and visualize it dynamically as well. And finally, with ArcGIS Enterprise, you can share your models and scripts as well as geoprocessing services. And these are web tools that you can share with others and can be accessed from ArcGIS Pro, web apps, and APIs. In the same way, you can also share your Raster functions to even ArcGIS Online and ArcGIS Enterprise to share the Raster analysis as well. And now I would like to go over to Tilmann Steinmetz from NIWA, and he can give us an example of how NIWA uses modeling and scripting in their sea, coast, and estuaries application.
Kia ora, my name is Tilmann and I work for NIWA. I want you to see a new app that we've built for a project called Seas, Coasts, Estuaries, New Zealand, or simply SCENES for short. It was co-funded in equal parts by the New Zealand government's Envirolink and NIWA. The reason why I think this is a cool app is that it uses a pretty unique combination of working with a large volume of raster data in an easy to use web application for doing pretty advanced data analysis. So my presentation has two parts. In the first part, I want to talk about the SCENES project and how we've designed the app to meet user requirements. In order to understand the technical background and how we've set up and structured what's essentially a raster database for the web, there's a complementary section in the imagery and drone session this afternoon. So in the second part, I will explain in a bit more detail what the raster data management for the app looks like. I'd like to encourage you to view both parts of this presentation to better understand the SCENES application. Now, let me first explain where this app has come from. The project required a public-facing app, a web app that can be used by councils and others for reporting on the state of the environment. Essentially, we needed a tool which would be able to make large volumes of raster data available in a timely manner. And besides being able to display spatio-temporal water quality data, there was also a need to analyze data in the app, as well as being able to export data for analysis using external processes. This would turn data into useful information for scientists, resource managers, and other interested parties. Of course, the app had to be as easy to use as possible, which is a little harder when you know that it will be providing access to information from literally thousands of rasters. The app in its current state gives users simple yet sophisticated tools to work with our science data. I won't be talking about the way these rasters have been derived from Modus Aqua satellite data. That's probably a topic for a separate presentation. The app allows users to interrogate ocean parameters for the assessment of phytoplankton biomass, water clarity, which is important for visibility or the depth of the euphotic zone, and the availability of light at the seabed, as well as temperature, suspended sediment, or seabed primary production and their development in time and space. Using a few simple to use tools, we enable users to select an area and time span of interest for efficient extraction of those water quality products to then either download for further analysis or using online tools that provide quite sophisticated statistical analysis and graphical interpretation. Analysis tools to work with the contents of our online raster database have been developed as a sort of a mix by utilizing the so-called WebAS widget tools, which stands for Web App Builder for Image Services, from Esri's GitHub pages, as well as using regular GP tools. The GP tools use either Python or R scripting, or both of them together. This is made possible by linking the two via the R ArcGIS bridge. We use Microsoft ROpen on the server to drive this process. Our libraries provide a host of sophisticated graphing, while Python is used in this context to give access to regular GP processing using ArcPy, as well as driving simple in and out processes such as reading and writing files. You can therefore think of the analysis tools as working at 3 different levels. Firstly, the WebAS widget tools provide out-of-the-box functionality to do something with image services, such as looking at the output of a particular rendering option or choosing a time slice for a parameter. These are JavaScript-based widgets which are installed into the Web App Builder developer version. On the map, the temporal development of parameters can be animated using a time slider. That's just the regular time slider widget in Web App Builder. Users can choose from a set of parameters and time slices by using the pre-configured app widgets, and those could be WebAS or regular widgets. One simple example is a temporal profile of a point of interest as shown in the lower left corner. The current imagery service tools from the WebAS GitHub repository work well, but their scope is a little limited, and we'd wish for them to be extended further. The temporal evolution of individual parameters for a single location can quickly be analyzed using a temporal profile, while external analysis is possible for larger areas by exporting the pixel values into a CSV file to use in other tools. And we enable that using a GP tool, which is shown in the upper right corner, which ultimately returns a CSV file for download to the user. Secondly, the ArcGIS bridge-based tools use the pixel data from the image service as input, which goes into an R script on the ArcGIS server machine to produce a static output chart or table that is returned via a link from a GP service. Users can access individual GP services in the web application to drive individual analysis types and create charts that can be downloaded, as shown on this screen. Thirdly, we can use a GP tool to export pixel data for an area drawn by the user from all time slices into a CSV file that can be shipped to an external server for more advanced analysis types and interactivity. This is currently work in progress, and at the moment it requires that the user downloads the CSV file after the export and copies it over to the other server manually. The Shiny Scenes analysis dashboard shown here runs as a separate web tool using an installation of R Shiny. It uses a series of analysis tabs at the top of the screen, providing the power of R and Shiny with flexible dashboards to drive interactive table and graphic output of useful analysis types. This brings me to the end of this part of the presentation. Please get in touch with us if you have any questions about this app or how you would use it. If you want to hear some more detail about how the data management works in this app and have a behind-the-scenes look, check out my second presentation this afternoon in the drones and imagery session. Thank you.
Thanks, Tilmann. And as Tilmann mentioned, he's going to be showcasing some more of the NIWA's Seas Coast Estuaries New Zealand at the drones and imagery session later on this afternoon. And you can also pop in and see NIWA in the sponsors tab of the virtual platform as well. So we have one last building block to actually have a look at. That is sharing and collaboration. And this is a particularly important building block because while we as GIS professionals love to do analysis and we love to have a look at machine learning and how we could use that in our processes, if we're doing all this analysis and not sharing our workflows and our results, there's really no point in actually doing the analysis. So how can we actually do this sharing and collaboration? Well, there's lots of different ways that we can do this inside of the ArcGIS platform. And these are just some of the ways. So we have the option to use ArcGIS dashboards to display the results of our analysis. And this is particularly useful when we have live analytics that we want to embed inside of our display. Another way that we could do this sharing and collaboration is through ArcGIS story maps. And story maps is really where we can tell those compelling stories about the results of our analysis. And Powerco, for example, has a really cool story map talking about their overhead power planning tool that we have heard about in this session. Another way that we could actually share our results would be using infographics. And this is where we use different graphics to represent the results of our analysis. Boudewijn has spent a little bit of time talking about Python notebooks and the use of Python in notebooks. And so these are really where we share our processes. So we can share our processes that we've gone to do our analysis. And I guess on top of that as well, we have Model Builder and we have some complicated other programs like the ArcGIS Bridge that allow us to share some of those more complicated workflows. We have ArcGIS Insights, where we can share a step-by-step model of our analysis, or create an interactive data story where people can come in and actually create their own story with the data that we have generated or the analysis that we have done. And through this all, obviously we're talking with ArcGIS dashboards, story maps, infographics. We're probably talking about the products of our analysis, but we also generate lots of data when we do analysis, and there's lots of ways that we can share our data on the ArcGIS platform. One of those ways is obviously through ArcGIS Online, and more specifically through the Living Atlas. And a way to have our data moderated with the metadata and share it out with the general public. And there are some examples of where NIWA has actually done this. So one example would be how they've shared their river environment classifications through Living Atlas. So those are just some of the ways that we can actually share the results of our analysis, the workflows that we've produced, or the data that we've produced as part of our analysis. Well, we've talked about what's possible. We just want to hand back to Esri, to Orhun and David to just take us through a little bit of what's coming in the ArcGIS platform for data science in ArcGIS.
Today, you have seen a small subset of the vast capability in ArcGIS Pro. It can be spatial data science or spatial temporal data science. We have extensive set of tools. And our way forward is enriching our platform so that for spatial data science, we have more and more tools that allow you to describe data, clean and wrangle data, to look for patterns in it and model complex relationships, while always having a strong integration with powerful frameworks such as Python and R. For spatiotemporal data, we have a brand new tool on forecasting time series, and also we are always actively working on powerful tools that allow you to understand spatiotemporal phenomena that you use inside ArcGIS, in addition to modeling spatiotemporal relationships. To have a better idea of our capabilities, here are some resources that you can utilize. These 3 links go to our spatial statistics page, where you can see the latest and greatest spatial statistics tools. The second link is our data science MOOC if you would like to learn more and enable yourself and your organization with these powerful space-time machine learning tools. And lastly is the link for our R integration, the so-called ArcGIS bridge. I highly encourage you to check out these links and explore materials created for you by experts in Esri.
So thanks for that, David and Orhun. Just got a slide here to sort of wrap things up with some URLs that you might find helpful, referencing some of the things that we've mentioned in this session. These resources are also available in the resources tab of the virtual platform, so you don't have to be scribbling them down right now. They are all available there in that resources tab. And don't forget that resources tab and the virtual platform will be available for 2 weeks after the conference finishes. And I just wanted to draw your attention to the MOOC that the Esri guys actually mentioned. So that's the Spatial Data Science MOOC. It is actually due to start again on the 28th of October this year. So do feel free to register for that if you'd like to actually go out and try out some data science methodologies. We now have a little bit of time for some Q&A. So let's just see what's going on here in our Q&A session. So if you have sent any questions through the virtual platform, they have been moderated and been released to us. If we don't get to answer your question, we will definitely follow that up post-conference with some answers. So where we've got a first question of, can you do machine learning outside of ArcGIS Pro and the ArcGIS platform?
Yeah, you want me to take that?
I think so, Boudewijn, that'd be great.
Yeah, so what Esri has been doing over the last couple of years is integrating machine learning inside ArcGIS, and that's either completely embedded in a tool or being able to reach out to machine learning modules. There's other ways to access that as well, and for example, you could just use Python and combine modules from ArcGIS and machine learning together. But also there is this ArcGIS.learn module in the ArcGIS API for Python, and that enables GIS analysts and geospatial data scientists to easily adopt and apply deep learning in their workflows. And that's trying to, machine learning can be hard to get started with, but that ArcGIS.learn module tries to simplify the process so it's easier accessible even if you're not a machine learning expert. So I hope that that answers the question.
I'm always interested that we've used or coined this phrase machine learning, but it's actually been embedded inside of the ArcGIS platform for much longer than that phrase has been around. So things like that regression analysis that David talked about, it's been around in the platform for years. I can remember my first ever course that I went on in, at Eagle was actually the regression analysis was something that we did on that. Okay, what's our next question? Will scheduling of ArcGIS notebooks come to ArcGIS Online? I think we might have answered that question during the session, but
yeah. So I mentioned it quickly. So it is on the roadmap. So currently you can schedule your ArcGIS notebooks in ArcGIS Enterprise, which is pretty powerful. So if you've got new data coming in, I don't know, every night data's being updated, like the notebook that I showed, where we pull in the COVID cases from the Ministry of Health, or any other data, you can schedule it to run overnight, or and update your analysis results by publishing the results back to ArcGIS Online. So every morning you got a new and updated map, and it is on the roadmap for ArcGIS Online. So currently you can actually use ArcGIS notebooks in ArcGIS Online. You can use the ArcGIS Python API, but also all the ArcPy modules in ArcGIS Online, and there it also comes back with a whole bunch of other modules to make use of. So that's a real powerful feature that is coming on, that you can actually schedule it in ArcGIS Online as well.
Yeah, so ArcGIS notebooks have just come out of beta in ArcGIS Online, haven't they?
Yeah. So they've been in beta for a little while, and currently they are since the latest release, they're actually released in ArcGIS Online, so ready to be used. And also good to mention is that if you open an ArcGIS notebook, is that on the top right, I believe it is, you can find a lot of sample notebooks as well. So that can be just for doing some data engineering, samples for managing your ArcGIS portal, but also some more advanced machine learning and deep learning examples, just to get either inspired or adapt to use with your own data.
I'm sure this question probably would come up if we had more time. What about, does it use any credits in ArcGIS Online to run any of the ArcGIS notebooks?
Yeah. So basically there's two types of notebooks, the standard and the advanced. So the standard is basically the ArcGIS Python API and all the other modules that are bundled with it. The other combines the ArcPy modules as well. And you can, if you look for credits and ArcGIS notebooks, you can find how much credits they actually use. But they are based off a credit model, and the reason behind it is that when you run an analysis, you actually let a computer do work for you. So instead of buying the computer that does the work for you, you basically pay for the work that is being done on the computers of Esri.
Oh, another question. Do you need ArcGIS Enterprise to do raster analytics?
So no, you don't need ArcGIS Enterprise. There's a lot of tools available in ArcGIS Pro that you can use, and very powerful ones are raster functions. So basically what they do is do on-the-fly analysis. So without creating an actual output, you can bring in satellite imagery. For example, what I showed with the burnt areas, as in you have a before imagery, after imagery, and you use raster functions to create that severity, that burn severity map. But also, and that's quite exciting, it's currently in a closed beta, but coming in the next, or maybe a release after, is imagery in ArcGIS Online. And that is not just sharing imagery layers. So currently you can create a cache of your raster data and publish that to ArcGIS Online. But at the moment you cannot publish an image layer to ArcGIS Online. So an image layer gives you access to the underlying raster data that you can then use in raster analysis. But in the plenary, Alice showed some of that coming up, and next to just the image services, it also brings raster analytics to ArcGIS Online. So you'll be able to do raster analytics straight from ArcGIS Online without the need for an ArcGIS image server, and you can use those tools then in ArcGIS Enterprise or in ArcGIS Pro, or you can use them straight from the ArcGIS Online map viewer.
Cool. Hey, I just this question had to make me smile, and it was, do you have to have a cool accent to do data science?
Well, I don't know if you need to have it. It could be an advantage, but I don't think it's a requirement to do so, to have it.
We've got quite a complicated question here as well. And it's, what is the difference between the classic supervised image classification, which has been available in ArcGIS for many years, and the machine learning version of it in ArcGIS Pro. And there's a comment after that question which says, because from what I've seen, you still have to teach the machine using samples.
Yeah, so basically what I believe is that the difference is the models that are being used to train that data. I'm a little bit outside of my comfort zone here, but there's different ways of training data, and in most cases you would still need training data in order to learn to teach the machine learning how to identify, for example, the palm trees that we saw. And
yeah, so can I just jump in there, Boudewijn? The algorithms that are used with that machine learning version are actually much more complicated than the ones that we've traditionally used for a classic supervised image classification. And they're more up to date as well, because obviously people are doing research in this area, and so that's continually evolving. And so Esri is trying to introduce that into its machine learning algorithms that they're using is to keep up to date with that research. But you're right, still needs to teach ArcGIS to actually use the samples that we've got.
Yeah, and I think there's another question coming in now. And that's looks to be on the sharing and collaboration side of things. So for dashboards, is it possible to create it in ArcGIS Pro?
So traditionally, ArcGIS dashboards are created in ArcGIS Dashboard, which is an ArcGIS Online app that we use. So the web map behind the ArcGIS dashboard, though, can be created in ArcGIS Pro and published from ArcGIS Pro, as can any of the services that you use inside of the ArcGIS dashboard.
Yeah, yeah, and I mean, if we talk about ArcGIS dashboard, that is that web application that we have seen in many presentations during the plenary as well. It's basically taking over the world in order to keep track of what is going on, because it gives you that map view, but also with all the tables and charts next to it. Of course, you can build dashboards without ArcGIS dashboards as well. If you use ArcGIS Pro, for example, that can use data that is being live updated, and if you have all the nice charts and tables in a ArcGIS Pro project, you could call that a dashboard as well. So there's different ways to look at the data, but in terms of the ArcGIS dashboards, yeah, that is built in the web application.
Yeah. Okay, well, I think that might be all the time that we have for questions. I've just got some final, I guess, follow-up little things. So I'm just going to switch back over to the slides here for a moment, and just want to thank all our presenters that we've had in this session. It's been amazing to hear from Powerco and NIWA. And thanks, Boudewijn, as well, for taking us through a whole lot of things. I'm going to leave you to read the slides, but in addition to what's on the slide, we are going to have a 30-minute break now. So time to have a break from your screen, get a cup of tea, take a bathroom break, connect with other conference attendees through the attendees hub, which would be a fantastic idea, or check out some of our sponsors and exhibitors. So 30 minutes, we expect you to be back in a second session if you're coming to a second session for 3:45 p.m. And once again, you have 4 sessions to choose from. So they are local government, field operations, utilities, ArcGIS for imagery and drones, and you can swap between those if you want to as far as the sessions are concerned as well, just like you could have for this first session. So thanks for being with us, and we'll see you back at 3:45.